true projects. In this video, we are going to explain about a project titled Diabetic Retinopathy Grading by Deep Graph Correlation Network on Retinal Images without manual annotations. So now coming to the introduction part, the integration of LSTM, BI, LSTM and GRU into the realm of supraventricular arrhythmia detection showcases the potential of deep learning techniques in revolutionizing cardiac health monitoring. These models' ability to capture temporal dependencies both in terms of short and long range patterns equips them to excel in identifying irregularities within ECG data. As technology continues to advance, further refinements and innovations in LSTM, BI, LSTM and GRU based SV detection are anticipated, contributing to more accurate and timely diagnosis in the realm of cardiac care. So now coming to the objective part for this project is to calculate or advancing the accuracy, efficiency and real-time capabilities of arrhythmia detection methods. By harnessing the power of these deep learning techniques, the research seeks to empower medical practitioners with more reliable tools for early detection and intervention, thereby contributing to improve patient outcomes and the broader landscape of cardiovascular healthcare. LSTM, BI, LSTM and GRU models except in capturing sequential dependencies and temporal nuances, making them well suited for disconcerting abnormal rhythm patterns from ECG data. The goal is to create robust models that can accurately distinguish between normal and abnormal heart activity, enabling timely medical intervention. So now coming to the requirement part, we have two types of requirements, that are hardware requirements and software requirement. In hardware requirement, operating system as Windows, processor i5 and above, RAM 4 GB and above is required, hard disk 20 GB and above. Coming to the software requirement part, Python IDE that is 3.7 version is required. So now coming to the methodology part, first data pre-processing. This step involves preparing the raw data for training and testing. It includes tasks like data cleaning, normalization, resizing images, handling missing values and splitting the data into training and testing sets. Second, run existing neural networks on IPACs. This involves taking pre-existing neural network models and applying them to the IPACs dataset. IPACs likely refers to a medical dataset related to eye conditions. Running existing models could involve fine-tuning or evaluating their performance on this specific dataset. Run existing neural networks on Messenger. Similar to the previous step, this involves running pre-existing neural network models on the Messenger dataset. Messenger could be another medical dataset related to eye health. Fourth, run proposed DGCN on IPACs. DGCN likely stands for Deep Graph Convolutional Network. This step involves applying a graph convolutional network model that you have proposed or selected to the IPACs dataset. Fifth, run proposed DGCN on Messenger. Similar to the previous step, this involves applying a proposed or selected graph convolutional network model to the Messenger dataset. Sixth, hybrid CNN with SMART processing. This step likely involves using a convolutional neural network in combination with a synthetic minority oversampling technique, that is SMART, to address class imbalance in the data. It generates synthetic samples for the minority class to balance the dataset. 7. CNN with iterative random forest. This could involve using a CNN in conjunction with an iterative random forest, that is RF model. The RF might be used to refine predictions from the CNN, combining the strength of the model. 7th, comparison graph. This step involves creating visual graphs or charts to compare the performance of different models or approaches. It could include metrics like accuracy, precision, recall or F1 score. 9th, predict test images. After training models, this step involves using the trained models to make predictions on a set of test images. The output could be classifications, probabilities or other relevant predictions. 10th, exit. This likely signifies the end of the program or process, indicating that the task or steps have been completed. So now coming to the execution part, to execute the project, first we need to open the code folder. Here we have a folder which is named as .ipnby file and it contains a dataset over here. Another folder named as encrypted IPACs. In this we are containing some images over here for eyes. And the folder named as encrypted Mesido, and this again we are containing some images over here. And in all these folders we are containing some images over here, and in this folder we are containing images for testing. And these all are the Python files which are containing the Python scripts in it. And here this is the run.bat file. Instead of executing the program in command line interface, we created Windows bat file to execute the project. So now to run the project, double click on run.bat file to execute the project. Here this is the graphical user interface. With this we are interacting with the program. Now click on dataset pre-processing button So here we have got the dataset which is pre-processed over here. And now click on run existing neural networks on IPACs. Here you can see that we have got a graph. Here x-axis represents false positive rate and here y-axis represents true positive rate. So now closing this graph, here you can see the accuracy over here, that is 94%. And now click on run existing neural networks on Mesido. Again you can see the graph over here that x-axis represents false positive rate and here y-axis represents true positive rate. Closing this graph and you get the accuracy of Mesido as 19%. Now click on run propose DGCN on IPACs. So now here you can see that we have got the accuracy for DGCN as 97.73%. And now click on run propose DGCN on Mesido button for getting the graph and for getting its accuracy over here. So here you can see that we have got a graph. Here x-axis again representing false positive rate and y-axis as true positive rate. So now closing this graph, you can see the accuracy for DGCN Mesido accuracy as 99.9%. And now click on hybrid CNN with smart processing over here for getting the graph and also for getting the accuracy of it. So here you can see that we have got the graph over here for smart hybrid CNN on Mesido AUC curve. Now closing this graph and you can see the accuracy as 99.5%. So now again click on CNN with iterative random forest button for getting the graph and for seeing its accuracy. So up to till now we have got the highest accuracy of DGCN Mesido accuracy over here, that is 99.9% in all these algorithms. So here you can see the graph for deep CNN with iterative random forest on Mesido data set AUC curve over here. Now closing this graph, you can see the accuracy for this is 99.8%. Now click on comparison graph button for getting the comparison between the all algorithms. So here you can see that x-axis represents the all algorithm names over here, and among all these graphs, all these algorithms, we can see that DGCN Mesido accuracy is showing the highest accuracy among all these algorithms over here. So now click on predict test images button over here for predicting the images. Suppose I am choosing this image over here and now click on open button to load the image. Here you can see that this is classifier as no dia. Now closing this image, you can identify with other images. Now click on predict test image. Suppose I am choosing this image, or suppose I am choosing this image over here. Now click on open button. Here you can see that this is classified as mild. So now close this image over here, and by clicking on the exit button you can exit with this application. So now coming back to the conclusion part. In the journey towards improved supraventricular arrhythmia detection, the collaboration between medical expertise and technological innovation becomes evident. The application of LSTM, BILSTM and GRU models exemplifies the synergy between data-driven insights and clinical acumen, fostering a new era in cardiac care. As these models continue to be refined and integrated into medical practice, the horizon of possibilities expands, promising a future where cardiac arrhythmias can be swiftly and accurately identified, ultimately saving lives and elevating the standards of cardiovascular healthcare. This adaptability, combined with their real-time processing capabilities, holds promise for transforming the way cardiac health is monitored, specifically in situations where timely intervention can be critical.
For updates on latest project videos, please visit True Project's YouTube channel and subscribe.